This video is going to be an introduction to logarithms, and I'm going to talk about what they are, where they come from, and we're going to do some basic calculations with them as well and look at some of the notation that we use for them. So I'm going to start with something a little bit basic, but hopefully you're going to see how it leads to something that's quite significant, that I consider to be a quite significant gap in your mathematical education. So to start with, we're going to look at these groups of numbers, and using mathematical operations, we're going to think about how these three values link with each other, okay, how they're all related with each other. So starting off very, very simple, we've got 2, 3 and 5. How do they link together? Can I write some sums down that use operations to link them? Well, you've probably already thought of them all. This is clearly addition and subtraction, isn't it? So I can write one sum down. Okay, using addition. I could also write the other addition sum that says 3 plus 2, but I'm going to leave that for now, okay, and you'll see why in a moment. But I've also got two subtraction sums. So 5 minus 2 produces the 3, and 5 minus 3 makes 2. Okay, so that's a pretty much complete set of sums that can produce each of these three numbers in turn. Okay, and to show how these operations link with each other, I'm going to put it into a formula triangle like this over here. So I'm going to put 2 and 3 on the bottom, 5 on the top, and addition and subtraction are inverses. I'm going to demonstrate that on the picture. So on the bottom, I can do 2 plus 3, but the order of addition doesn't really matter, so I can put a double-headed arrow like this to show that I can add in any direction, and that's going to make the 5 at the top. On the sides of the triangle, these are the subtraction sums. If I take the right-hand side, I have to subtract in that direction to produce 2. So that's my subtraction sum over there. And on this side, similarly, I have to subtract that way around to produce the 3. Okay, so there's a formula triangle that shows how addition and subtraction are inverses. Okay, moving on to the second part. Okay, I've got 2, 3 and 6 this time. Okay, how are they linked? Well, hopefully you're already ahead of me. You've probably noticed that it's this time it's multiplication and division. So we've moved up in the hierarchy of operations here, but I can do something very similar. I can write down at least 3 sums. Here's one of them. Again, I can change the order, but I don't need to. I've got a sum that produces 6. I can do 6 divided by 2, and that makes the 3. And I can do 6 divided by 3, and that makes the 2. Okay, so it's very similar. You've got multiplication sum and then 2 different division sums. And again, I can put that into a formula triangle. I can put 2 and 3 and 6. Multiplication on the bottom, but it works both ways round. I can do 2 times 3 or 3 times 2. But then I have to do 6 divided by 3 that way, and I have to do 6 divided by 2 that way. Okay, so again, multiplication and division, they're inverse operations as well. Right, the question is, can we do the same with my third set? Okay, again, I'm going to move up a step in the hierarchy of operations. And you've hopefully spotted at least one of these sums that link 2, 3 and 8, one of which involves powers. So 2 to the 3 makes the 8. Right, that's one of them. Now, my aim is to try and get 2 more sums so that I've got a complete set of all 3 of my numbers on the right-hand side here. So I've made the 8. Can I write a sum that produces either of these 2? Well, if we're thinking about inverse operations, I know that I've done a cubing sum here, and we know how to find the inverse of a power sum. That's to take a root. So I can do a cube root sum, and that combines the 3 and the 8 to produce the 2. Okay, but then the question is, what's the third one? What's the sum that produces the 3 by combining the 2 and the 8? Okay, and this is where there's a gap in what you've been taught before. Okay, you haven't actually come across this operation before unless you've seen it on your own. For now, I'm going to put a question mark, but you can probably guess the name of it because it's at the top of the screen. Okay, for now, we're going to put the numbers into my formula triangle, 2 and 3. Okay, 8 at the top. On the bottom, this time, there's a power operation, but it has to go in that direction. Okay, 2 to the 3 makes the 8. If I reverse the order, 3 to the 2 doesn't make 8, it makes 9. So So this is my power sum. I'm going to put box to the box. Okay. On this side, I can combine the 3 and the 8 using a root. That's one of the inverse operations. And I'm going to put the arrow this way this time because I think the way we write a root sum, the 3 comes first, then the 8. So I'm going to do this as a root. Okay. On this side, this is the important one. The operation that combines these two to make the power, that's what we call a logarithm. Okay. To combine these two, this is what we write. We write a log, short for logarithm. We need a base, and we need a number that we're trying to get that number raised to make. Okay, so this pink sum is called a logarithm. All right, and to make it, the base of my sum is 2, and what I'm trying to produce is 8, and I'm trying to ask what the power is, so we write it this way. So this is what I'd write down for my third sum. Okay, so the way that you read this, you say log base 2 of 8 equals 3. Okay, the 2 is the base. And this over here, the logarithm itself, produces a power. So I think the best way to read this statement is to say, what power of 2 makes 8? And the answer is 3. Okay, and that's a logarithm. So now you know your new sum. Try and find that button on your calculator and try typing that in and try a few more examples so you can get the sense of how it works. Okay, so now we've got a new operation to use. Okay, this is the power finding operation. If I've got an equation like this, x squared equals 40, you've got to think about what operation I've used. This is the power operation. To undo that, you'd know to just take the square root of both sides. We're going to ignore the negative solution for this one. I'm just thinking about what operation I need to use. You can predict it before you type it in, and you'd predict something about that's like 6 and a bit, and that would be correct. If you take the square root of 40, x is 6.32 roughly. Okay, these equations are all very, very familiar. These type of equations, they'll be less familiar to you. Okay, but now we've got the logarithm operation that helps you find powers now. So how you think of this is to find the power, we can apply something to both sides, but it's not a root this time, it's a logarithm. So I'm going to take logarithms of both sides. And what's the base of my logarithm? Well, the base I'm using is 2. Okay. And I'm going to put 40 in because I'm trying to find the power of 2 to make 40. Okay, so to both sides, we're saying we're taking logarithms base 2. Okay, taking logarithms of this produces x, the power. This is the solution. Okay, so what power of 2 makes 40? You can predict it because we know that 2 to the 5 is 32, which is too small, and 2 to the 6 is 64, which is too big. So we can predict that it's probably going to be 5 and a bit for the power, and you type it in, and as we have guessed, it's 5.32. Okay, so that's how you find a power. But this notation is important. It's important that you know how to write things down and how we read it and what it all means. Okay, so I'm going to generalize what we've done a little bit, and we're going to think about what it all kind of means. Okay, so in general then, this is my kind of general case. This is what I'm trying to figure out what this all means. So the logarithm base a of b, well, the whole thing is working out a power, okay? Think of a logarithm as just what? A power. So this is asking what power of a makes b. If I assign a value to this, if I say that this has a value of x, okay, and this is saying that the power of a to make b is x, I can then write this as, rather than a logarithm statement, I can write it as a power statement, okay, an exponential statement. So the equivalent version of writing this down is to say that if I raise a to the power of x, then that makes b. Okay, take a moment to think about how you go from this side to this side. The power of a to make b is x. That's what it says over there. Okay, so hopefully we can see how the definition works and we can figure out some examples. Let's do the left-hand side first. So log base 3 of 81. What power of 3 makes 81? Well, the power of 3 to make that is 4. Okay, and that's because the equivalent statement is to say that 3 to the 4 makes 81. Okay, we've worked out the power. Okay, log base 10 of 1,000. Base 10 is quite a common base to use when we're using logarithms, okay, because it applies to our decimal number system quite well. What power of 10 is this? Well, it's 10 to the 3. So 3 is my logarithm. Okay, and that's because, I'll write it under here, 10 to the 3 is 1,000. Okay, if I give you a couple of seconds to think about this one, think about what the answer to this one might be, and I'll tell you in a second. Okay, so we're looking for a power of 9 to make the third. It's taken a reciprocal of the 9 and it's square rooted, so it looks like the power is minus a half. Okay, and you can write another power statement that represents the same information. The power of 9 is minus a half, and that makes a third. Okay, so that's how the basic definition of a logarithm works. You can do all of these on a calculator. It's worth noting that the base that we use is always going to be a positive number. Okay, it doesn't really work to have a negative base, and you can maybe think about why. And also, we don't often like to have 1 as our base as well. So whenever we see the base down here, it's always a subscript, and a is positive, and we never have it equaling 1. Okay, and again, you can think about why. Powers of 1 don't get you very far. Okay, it's difficult to produce anything other than 1. Okay, a couple of special cases. If I have log with any base, base a, to produce 1, then the log base a of 1, well, what power of a makes 1? That's going to be 0. Because a to the 0 always makes 1. Okay, and similarly, log base a of itself, if it's log base a of a, then the power of a I need is 1, because a to the 1 makes itself. Okay, I can generalize this one a little bit further as well, just to make it a little bit more complex. If I have log base a of, let's say, a to the k, if it's written in that form, then, well, what power of a is this? Well, the power of a that's there is k. Okay, so it's as if the log base a here and the a there are cancelling out. Okay, it's like you've done that, and that's exactly what the logarithm is doing, because it's the inverse to exponentiation. Yeah, we've described it as an inverse operation, okay, when we started it off. With these three, what I want to do is I want to do the opposite of what I did over here. Can we write this as a logarithm statement? Okay, this is the exponential statement. Can we write the logarithm down? And that's going to make the power. So let's write log down. Okay, what are we taking powers of? Okay, well, the base is 5, so that's the base of my logarithm. And what am I trying to produce as a power of 5? I'm trying to make 25. Okay, and together, the power that that produces is 2. Okay, for this one, this is similar. So it's the same statement you'll notice, but in reverse. This time I've made the base 25, so it's log base 25. I'm trying to make 5 with that, and the power that I need is a half. Okay, now just to stop for a moment, I've done these two linked together for a reason. You might want to write down, as a bit of a challenge, a general statement that shows what happens when you switch these two numbers around. Okay, if I switch the base, okay, and the number in my logarithm, what happens over here? Okay, and it's reasonably obvious from the example. See if you can write down a general statement that looks a little bit more like this. Okay, if I've got log base a of b, what happens if it then becomes log base b of a? Okay, see if you can do that. And then finally, similar to these top two, I'm going to write a logarithm down. Well, it's log. The base is a third. and I'm trying to make 27 with that. And the power, all of it at once, the logarithm is -3. Okay, so hopefully you've got an understanding now of what a logarithm is, it's a power, and how we write it down and what the notation is that we use. Okay, best of luck with the questions.